Hello. With due regards to the chair, let me start presenting the work. Myself, Arghya Bandyopadhyay, Associate Professor of Department of Mathematics, Kolishani College, affiliated to the University of Burdwan, India. The title of my talk, as you can find, Tsunami Wave Motion due to a periodic ground motion on a non-uniformly sloping beach. Here, we will be dealing with an analytical study of tsunami generation and propagation. Our work is mainly mathematical and deals with the hydrodynamics of the problem. Now let's share a few words on the background and the motivation of the work. Tsunami research is different from the other extreme natural hazards, mainly for two reasons. We find mathematical models are not easily available. Here in the third bullet, you see that I have highlighted that non-uniform bathymetry part. The word non-uniform is highlighted because non-uniform bathymetry is not taken in a mathematical study of tsunami waves because it brings additional constraints into the study which are difficult to handle. But we have taken the courage to include these feature into our analytical study. Prior to Boxing Day tsunami, instrumental recording in open ocean was not available, but now we do have a huge real-time data at our collection. Our aim is to underscore the effect of bottom bathymetry on the motion and also to highlight other features of motion not known even with uniform ocean slope. Now let's provide the outline of today's presentation. But before that, please take a note on the figure that is on the screen to understand the physical setting of the problem. We take the vertical upward direction as the y-axis and the undisturbed horizontal surface of the sea as the xz plane, of which the axis OZ is along the shoreline. Ocean is supposed to be bounded by a beach of variable slope given by the equation y equal to minus qx to the power r. We are dealing with classical beach problem of hydrodynamics. The next point, novelty of our study is in inclusion of the non-uniform bathymetry in an analytical model. The non-uniform bathymetry will dissolve the uniform bathymetry, rather the uniform bathymetry will dissolve out from our physical setting to include the non-uniform bathymetry of the model. Shallow water wave theory is the basis of our model. Analysis of wave integrals and to reduce it to a computationally tractable level is our next motto. We will study the existence of the forerunner and provide a measure of the run-up. We also want to study the effect of bathymetry over the motion at different time span. Now we will show the equations of motion. Linear shallow water wave equations. This is the equation of continuity and this is the equation of motion, and this is the initial condition, initial surface displacement and initial surface velocity. Now if we eliminate u from the above two equations, then we will arrive at this partial differential equation, which is the forced longlinear wave equation. For the solution to be physically reasonable, we note that we must put a restriction on r. R should lie between 0 and 2. Then by the method of Hankel transform, we obtain the solution of the wave integral as this. Tak and Wang in 1972, in a seminal work published in JFM, have shown similar type of solution, but their solution was obtained for a uniformly sloping beach. If we put r equal to 1 in this solution of ours, then we will arrive at the solution given by Tuck and Wong. Here, zeta 1 is given by this, and these are the parameters of which nu is very important in our context, and this is the dispersion relation. After evaluation of the S integral, it seems that the integral should be split in two parts, one from 0 to xi 0 and another from xi 0 to infinity in xi integral. To obtain two parts of the wave integral, one is eta 1 1, another is eta 1 2. So 0 to xi 0 is the one part, and it is the eta 1 1 component of the wave, and xi 0 to infinity is another part, which is the eta 1 2 of component of the wave. The analysis of the wave integral eta 1 1 gives us the following form. This eta 1 1 has been shown in one of our previous publication, acts as a forerunner, and this comes ahead of the actual forced wave. In fact, the existence of such forerunners is actually observed in 2011 Tohoku tsunami. The analysis of the integral eta 1 2 ultimately provides a four-wave composition of eta. Here, the plus minus sign indicate corresponding expressions for nu greater or equal to 0 and for nu less than 0 respectively. While eta 1 1 we have shown, but the eta 1 2 expressions are really complicated, and they are not shown in this presentation. If you are interested, you can find those in the extended abstract. For a mathematically inclined researcher, please note that the complicacy lies in the double Hankel integral expressions of eta 1 2, which have been analyzed here by some daunting mathematical exercise. But what happens when t is greater than tau is interesting. We find that for t greater than tau, similar four-wave component is added with the previous wave quartet. So the form of the wave quartet structure still prevails when t is greater than tau, with another wave quartet joining the system with a time lag of tau. In the next few slides, we'll discuss these results through several illustrations. Now, to illustrate our results, we consider one particular periodic bottom disturbance, and it's a general Gaussian in nature. And we have also taken r equal to 0.8 and r equal to 1.1 to include two different types of nu less than 0. That means when the ocean bottom is convex upwards, and when r equal to 1.1, then nu is greater than 0. So it shows that convex downward profile respectively. The nature of eta 1 1 and eta 1 2 are shown near the shore, and it is observed that at the subquake range, that is when t is less than tau, eta 1 1 dominates the wave spectrum. This eta 1 1 comes ahead of the forced wave, and these are the forerunners. Here you find that eta 1 1 dominates eta 1 2 when t is less than 150, which is the value of tau here. Well, in the second of the illustration, second slide showing the illustration, we find that eta 1 2 3 is the region of wave evolution at shore, and it dominates the wave spectrum after a certain time t greater than tau. So to our understanding, eta 1 2 3 can be taken as the analytical measure of runoff in case of generation of tsunami in a physical setting similar to the one considered here. We have taken here r equal to 0.8, and tau is tau is 150, as in the 152nd as in the last illustration, and So this eta 1, 2, 3 acts as a measure of runoff. So this is very interesting. The third illustration of the we show the nature of the wave portion eta 1 to 1. The oscillatory growth of eta 1 to 1 increases as the wave approaches the shore. You see, this is the graph, and one interesting feature is the combined effect of the three waves of eta 1 2, which is actually conquered by eta 1 2 3 at the shore. It enhances its effect when eta 1 to 1 and eta 1 to 3 match. So when the phases of eta 1 to 1, eta 1 to 3 match, then eta 1 2 3, the measure of runoff, this runoff will even increase when these two match. In this last illustration, we will show the effect of bathymetry on the wave evolution. And this is very thought-provoking fact. And we find that when the ocean bottom is convex upward, then the wave at the shore will be of the nature wave elevation, and when the ocean bottom profile is convex downward, then we will find that wave depression will first follow. So this is very interesting fact that is being revealed in this study. Now we come at the conclusion of this presentation. In an analytical study, we provided a solution which is valid for all time t in a non-uniformly sloping beach while dealing with a tsunami wave motion. Our result shows four very important things: that waves behave in a quartet, and from this quartet we have been able to isolate firstly forerunner, then we have been able to isolate the runoff, and last but not the least, we have been able to show that ocean bathymetry affects the wave evolution, whether elevation or a depression of wave, with respect to whether the ocean bottom is convex upward or convex downwards. In Tohoku tsunami of 2011, we did find forerunners, observational findings matches with our mathematical findings. Needless to mention that ocean bottom is far from uniform, and it may not be in a general parabolic shape as we have considered, but our generalization acts as a first step to include complex bathymetry in an analytical model. This is the bibliography. Thank you. I convey my sincere thanks to the conference authority for providing me an opportunity to present our work in front of an international audience in this virtual mode. And thank you all for listening me out for the last 13-14 minutes. Thank you.